Okay, we are going to be moving on here to 17 and our big day of electrochemistry. So in this chapter, we're going to talk about redox reactions, oxidation states, balancing redox reactions. We'll get into galvanic cells, a little bit about batteries, and some electrolysis towards the end of the chapter. So the first part, we're just going to kind of go over some of the parts here just to make sure hopefully everybody is on the same page in terms of redox reactions and so forth. So basically, redox reactions, right, are oxidation and reduction reactions. And they always basically occur together. So something gets oxidized, something gets reduced. And there's several definitions of oxidation and reduction. Oxidation can mean the loss of electrons. It could also mean that you gain oxygen going from the reactant side to the product side. Could also mean that you lose hydrogen going from the reactant side to the product side. While reduction is pretty much the opposite there, it is when you gain electrons. It's when you lose oxygen going from reactant side to product side, and when you gain hydrogen as you go from reactant side to product side. So for the most part, in sort of general chemistry, most of the time we do focus in on really the electrons either being lost or gained. And when you go to organic chemistry, if you take that next, sorry about that, but if you take that next, that is where you will see oxygen and hydrogen used a lot when you're dealing with nonmetals. And organic chemistry, sort of the gaining and the loss of oxygen is very much sort of followed in a lot of reactions. But here we kind of do the gain and loss of electrons, and that's people's favorite things, which is the lion goes grr, right? Loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. Clearly, you could put the Leo the lion on the oil rig and he'll go grr, so you don't have to choose. You could just use them both, I suppose. But we definitely will look at really electrons being gained and lost. Redox reactions, as you may remember from the first semester, are really sort of a broad class of reactions, sort of a big category of reactions for which you can more specifically classify reactions. And as you might have learned, a lot of redox reactions are reactions like synthesis or combination reactions, decomposition reactions, single replacement reactions, combustion reactions. They all really fall sort of underneath the umbrella of redox reactions. And really the transfer of electrons is one of the reasons, or one of the sometimes referred to as the driving forces for why reactions take place, is actually that transfer of electrons. The other two driving forces for reactions is the formation of a precipitate or a solid and the formation of water. And those usually are your precipitation reactions, and your acid-base reactions, which fall under the big umbrella of double displacement reactions, is sort of where those guys sort of fall. Now, when we talk about sort of electrochemical sort of processes and really these sort of gaining and losing of electrons, or transferring electrons really, we oftentimes will kind of use the electrons as they are being transferred, perhaps to go out and do some type of work, you know, like for example, similar to when you put a battery in the battery compartment, there's a wire, right? The whole redox reaction sort of happening. Electrons go out, power the device, and help sort of convert it. I do some type of work there by those electrons being basically moved. This reaction right here, which is actually a synthesis reaction, it's actually a combustion reaction as well. So this is a synthesis reaction. It is also a redox reaction. And if you're not sure, you know, what is being oxidized or what is being reduced, there's several ways you could figure it out, but I'm like the sort of very simple process of you can make like a number line if you're not sure. And usually to the right side of 0 are positive numbers, left side of 0 are negative numbers. So when something gets oxidized and it loses electrons, does it become more negative or more positive? If it loses, yeah, it becomes more positive. So if you find somebody on the left-hand side of the arrow there that goes from the left-hand side to the right-hand side where their oxidation state actually becomes more positive, then they are going through oxidation. Obviously, the opposite would be true if something sort of gained electrons. You have more electrons than protons, perhaps, and you would become more negative. So if you look at something on the left-hand side to the right-hand side and compare their oxidation states, our numbers, and it becomes kind of more negative, it is going through reduction. So when we look at something like this, a reminder that when something is pretty much by itself uncombined, it has an oxidation number of 0. So the magnesium over here has an oxidation number of 0 or an oxidation state of 0. The oxygen here also has an oxidation state of 0. They do not have charges when they are by themselves. It's only when a metal and a non-metal come together that they actually do gain a charge. And on the right-hand side, the magnesium ends up with a +2 and the oxygen ends up with a -2 in this case. So if you weren't sure, you could use your number line there. And if we look at magnesium, it starts at 0 and it ends at +2, which means it is moving definitely in the more positive direction. And it is the magnesium here that is going through oxidation. By the way, the nice beauty thing of redox reactions, right, is once you identify one, the other guy is doing the opposite thing. So by default here, the oxygen is going through reduction, but you could do the same thing for the oxygen. It is starting at 0 there on the left-hand side, and on the right-hand side, it becomes -2, which means it is moving in that direction, which means it is becoming more negative, and it is becoming or being reduced or going through reduction here in that way. So that's a really sort of simple way. If you're not sure, you can just kind of move whichever way the oxidation state is moving. If it's becoming more positive or more negative, it will tell you if it's being oxidized or reduced. Any questions on that there? Now, the more really simpler way is, and especially in a situation like this, that is a metal and a non-metal, right? And always when a metal and non-metal get together, it is the metal that should lose electrons, right? And the non-metal should gain electrons. So in an ionic situation, it always should be the metal that is going through oxidation, and the non-metal here is going through reduction. But you will come across things where you got multiple metals sort of happening at the same time. So, sometimes you need to sort of figure it out. When we look at the overall reaction, which is obviously above here, we can actually break this apart into what are referred to as half reactions. And they're half reactions because they're basically half of what's going on. One half is the oxidation half reaction. The other one is the reduction half reaction. So in this particular case, this is the magnesium is going through oxidation. Again, going from 0 to +2 here. We will have magnesium going to magnesium with a +2. And in this case, 4 electrons being given off. And we know this is the oxidation half reaction because we see the electrons always on the product side in a oxidation half reaction. It is 4 electrons because you got 2 magnesiums, right? Each one loses 2. That's a grand total of 4 that's actually being sort of transferred in this particular case. On the other side here, we have the oxygen that's going to basically pick up those electrons or gain those electrons. And that will give us our reduction half reaction, which in a reduction half reaction, the electron should always be on the reactant side. Any questions on that there? Now, they're half reaction because, frankly, if you had the half reactions, and maybe not the overall reaction, you could simply add both of those reactions back together, and you could get, obviously, the overall reaction that is taking place. before you ever add together a oxidation half reaction or a reduction half reaction, there's one thing you should always make sure, and that is that you have the same number of electrons in each half reaction. And sometimes that may require you to multiply a half reaction by a number. And it may also require you to multiply both half reactions by a sort of a number to get to the equal number of electrons. The idea of this is it is sort of a complete transfer of electrons, which means however many electrons in this example, the magnesium lays up, should be the exact same amount of electrons that the oxygen gains. So it should be like a perfect transfer. And that means every time that you do add together your two half reactions, they should always completely cancel out. You shouldn't have any electrons left over. If you do, you definitely did something wrong there. And by the way, when we add these together, like kind of normal, anything on opposite sides of the arrow that's the same could either completely cancel out or reduce down. So in this particular example here, the electrons obviously would completely cancel out. Everybody on the left-hand side of the arrow stays on the left-hand side. Everybody on the right-hand side stays on the right-hand side. And these are really two ions that are going to come together to make our magnesium oxide, our little white solid, if you do this reaction. When you burn magnesium in like a Bunsen burner and they tell you to observe what happens, but without looking at it, because it's a very, very bright light and you'll be blind if you kind of look at it and then stare at it directly. My always favorite instructions, observe what happens, but don't look at it as it's burning and stuff like that. Any questions on that there? Okay. So obviously here's our half reactions as we just talked about, adding those guys back together. Another example is another synthesis or combination reaction or another really combustion reaction. By the way, the basic definition of combustion is it just needs O2 on the left-hand side. Although when we think about combustion, we think about kind of the organic combustion reaction. But again, this is also a redox reaction. Here on the left-hand side, our calcium is 0 in terms of its oxidation state. Oxygen is also 0. The calcium is +2, and the oxygen here is -2. So once again, if you weren't sure, you could just kind of follow what's going on. For our calcium is starting at 0 and ending at +2, which means it is moving in the positive direction, which means it is going again through oxidation, as we would expect it to do, since that is the metal. The oxygen is starting at 0 and ending at -2, heading in the negative direction, which means, again, the oxygen here is going through reduction in this particular case. We got our half reactions here again. This would be our oxidation half reaction. We know that once again, because our electrons there are on our product side, this would be our reduction half reaction, the second guy. We have our electrons there on our reactant side. Once again, these electrons will cancel each other out, giving us the overall reaction that basically occurs when we add both of these guys together. Also, very much like the magnesium example here, we have two calciums. Each one, again, is going to lose 2 electrons, which is why we do have 4 total electrons. You should always, balance everything. Yeah, so you should balance the overall reaction if you're starting with that. That way you get the correct number of electrons and all that good stuff. Actually, if your electrons are off and you do need to multiply each half reaction by a number, that will kind of balance it for you, actually, when you do that and you get the right number of electrons. And then when you add them back together, you'll be in good shape. Any questions on that there? Now, we also, when we talk about oxidation and reduction reactions, we do talk about reducing agents and oxidizing agents. And the reducing agents and oxidizing agents are different than what is being oxidized and what is being reduced. They are basically opposite of their names. So the oxidizing agent is the guy that is being reduced, while the reducing agent is the one that is being oxidized. The reason for that is, for example, the guy that is being reduced needs to gain electrons. In order for it to gain electrons, somebody else needs to lose electrons, and that means that guy is going through oxidation. So it is causing the oxidation in the other species, so it can lose those electrons so it can gain them. And vice versa, the guy that's being oxidized will need to lose electrons. And by the process of it losing electrons, there's got to be somebody to gain those electrons. And when it gains those electrons, it will go through reduction, which is why it's known as the reducing agent. So in our two examples there that we just looked at, we had our magnesium plus some oxygen, little magnesium oxide action, and our calcium plus some oxygen, little calcium oxide there. And in this case, this guy here and this guy here, they were both being oxidized, which means they were both are reducing agents in this case. By default, that would mean this guy is being reduced, which means this would be our oxidizing agent in each of these examples. When you're asked to identify a reducing agent, an oxidizing agent, what is being oxidized and what is being reduced, they are all found on the reactant side. That is where you find those guys, not the product side. So you find them all on the reactant side. Those are pretty much what you do. So when you are asked that question, you do want to be specific. You just don't want to write, write like, I don't know, like magnesium, something like that, So you want to make sure it is, just the magnesium, or if it's something that had a charge, for example, if this was being reduced, you want to make sure you would write it with the charge and stuff like that. But again, they should be found on the reactant side, all those things, not really the product side, because at that point, they've already done whatever they were going to do over there. And that's sort of the end product that you have. Any questions on that there? Now, as I mentioned before, we don't really run into it too often here, but again, the other definitions of oxidation and reduction, which is the gaining of oxygen or losing of hydrogen, which is the definition of oxidation, and the losing of oxygen and the gaining of H2 is reduction. So if we looked at, for example, our tin over here, from the left-hand side to the right-hand side, it has lost some oxygen. And when it loses oxygen, that is a definition of reduction. Over here, the carbon to the other side, the carbon has gained some oxygen, and that is a definition of oxidation. That is why in this example, the carbon is our reducing agent, because it is the thing that is going through oxidation. And our oxidizing agent would be this guy right here, really the tin as well. Now, the nice thing about this particular one was there's actually a metal there, so you could actually still do the sort of oxidation states. We just look at the guy that had the metal, which was the SNO2 going to our SN. The charge on the SNO2 here is +4, yes. Oxygen -2, and there's 2 of them, right? So that's +4 and 0 here. So once again, if you were looking at just a 10, actually started at +4 and moving towards 0, moving in the negative direction, it is going through reduction as we identified before. So in this particular example, because there was still metal, you could actually look at the metal and figure out what's going on. And like I said, if you were able to figure out that was being reduced, you would know by default the carbon would be going through oxidation. So that's one of the nice things about it is you just need to kind of figure out one. You could pretty much figure out what's going on with the other guy that is there. Any questions on that there? I got the charge of 4 because this is an ionic compound, so you could just do it like an ionic compound. The charge on the oxygen is -2, right? And there's 2 of them. It gives us a grand total of -4, and there's only 1 tin, so an ionic compound needs to equal 0. So to balance it out, it would have to be +4 in this case. Yeah. Other questions? So let's talk about oxidation numbers or oxidation states and officially sort of how to properly assign these guys. When we talk about oxidation numbers, as I mentioned, sometimes referred to as oxidation states, these are the charges in the atoms would have in a molecule or an ionic compound if the electrons were completely transferred. So sometimes people have a really hard time with oxidation numbers and states because up to this point, it's been beat into your head that certain elements make certain charges, like chlorine is always -1 and all that good stuff. But that is definitely true when you're dealing with an ionic compound. So everything that was beat into your head about ionic compounds is still true. If you have an ionic compound, you know, the charge on the elements in there will be the oxidation numbers. It's really when you get into a more covalent compound where you got sharing of electrons that sometimes elements will take on sort of a different charge in that orientation where they're sharing electrons depending on obviously who they're sharing electrons with, what type of bonds are sort of happening and all that kind of stuff. And that's really what the oxidation state is. So for example, something like chlorine can be -1 in an ionic compound, but it could be like, you know, +1, +3, you know, +6, you know, and depending on what it's attached to. So it can have different oxidation numbers. So it's not always what we sort of visualize as the charges like we think about in an ionic compound. So let's talk about the actual rules for properly assigning them. The first one's pretty simple. If you got pretty much anything that is in its elemental form, it is not combined with anything, it will have an oxidation number of 0. So if you got any type of metal that's by itself, it's going to be a 0 starting one. You know, some diatomic molecules like H2O2, those guys is again naturally how they come. They will also be 0s. If you have any monoatomic ions, they're just sort of by themselves, if you will, or again in an ionic compound like iron 3 chloride, the iron would still be +3, would be its oxidation state as well. Now, a lot of times when you're assigning oxidation states, oxygen is oftentimes involved, and that's usually a really good place to start with when you're assigning oxidation numbers. Pretty much in most cases, oxygen will be -2. The one exception would be if it's actually peroxide, which is this guy right here. It's a polyatomic ion. And it would be -1, like we see here in hydrogen peroxide. So how do you know it is sort of peroxide? So a lot of times you'll have that extra 2 kind of hanging out there in the formula. You know, sort of how you know. But I would say probably in most cases, if you see an oxygen, it's probably going to just be oxygen, you know. But, you know, if it's hydrogen peroxide, maybe some sodium peroxide sometimes pops up and stuff like that. You know, it would be technically -1. Now, the oxidation number of hydrogen is always +1, except if it comes in a binary compound after a metal. So that's like our good friend, like LiH, that is lithium hydride. That's the negative version there of hydrogen. Lithium is +1, hydrogen is actually -1 here. But pretty much if you have hydrogen and anything else, it's going to be pretty much +1 in those cases. Anybody from group 1 and group 2, is there normal +1, +2 type of oxidation numbers? Fluorine is always -1. Now, when we add up all the oxidation numbers for each of the elements within a particular compound, molecule, or ion, it does need to equal the overall charge. So if you have something that has no charge overall, when you add up all your oxidation numbers, they need to equal 0. If you have something obviously that has like a -2 overall charge, when you add up all your oxidation numbers, it needs to end up being -2. So if we look at our good guy here, which is a little bicarbonate, like I said before, usually when you got like a situation of 3 here, it's usually a good idea, especially if there's oxygen involved, to really start with the oxygen and kind of go outside, and save the guy in the middle for the end is usually the good move of sort of assigning oxidation numbers. So oxygen here would be -2 in this case. And there happens to be 3 of them, which gives us like a -6 overall charge there. Going to the other side, which is hydrogen, which is +1, gives us a +1 over here. That means, though, that this whole thing has an overall charge of -1, which means when we add them together, we do need to end up there at the -1. That means in this particular case, I believe carbon here needs to be +4 to do that. +1 and +4 is +5, -6 leaves us a -1 overall charge here. Now, if you were to give the answer here, the proper answer would be hydrogen is +1, carbon is +4, and oxygen is -2. Those are the proper oxidation numbers or states for each of these things. You do not give the grand total like -6 or anything like that for oxygen. It is basically one guy by itself, what his sort of charge would be. You also need to, when they are oxidation numbers, give the charge. Even if it's positive, you should write +1, +2, or -1, -2, whatever it may be. So you should give the charges with it. Any questions on assigning oxidation numbers here? Okay, so why don't you try a few here on the next slide and see what you come up with. Come up with the oxidation numbers of everybody that's there for each of those guys. Take a look. So first one there is lithium oxide. It's really an ionic compound. So the nice thing about ionic compounds is pretty much the charges are going to be the oxidation numbers. So we hopefully know that oxygen, once again, should be -2 here. And lithium, which is a member of group 1, should be +1. So our lithium should be a +1 oxidation state, and our oxygen there should be a -2. Looking at the next one, which is PF3, here we don't have oxygen, but we could start with fluorine. Fluorine is always going to be -1. And there's 3 of them, which gives us like a -3 overall sort of charge. There is no overall charge on PF3, which means to balance it out here, the phosphorus is a +3 oxidation state in this arrangement. So the phosphorus would be +3 and the fluorine would be -1. Now, again, you might have learned when you talk about ionic compounds that phosphorus will be -3. But again, in this arrangement, sharing electrons with the fluorine, it actually takes on a positive sort of oxidation state for sharing with all those fluorines. That is because fluorine is more or less electronegative. More. So those fluorines are taking the electrons, making the phosphorus in this arrangement more electron deficient and thus more positive in this case. Any questions on that one? HNO3, again, here in a situation of 3, you would start with the oxygen is a good idea. That's -2. Give us a -6 overall. Going to the other side, we got hydrogen, which is +1. In this particular case, we need equal 0 since there is no charge. That means, once again here, our nitrogen actually will take on a +5 arrangement, if I did the math right there. Hydrogen would be +1, nitrogen would be +5, and oxygen, once again, would be -2, not the grand total, but just -2. Any questions on that? Lastly, here we got a little dichromate action happening. That's a -2 there for the oxygen, gives us a -14. We do need to end up being -2 overall because of that. There happens to be 2 chromiums. That means each chromium must be +6. Yeah. So each chromium does need to be +6. That gives us a +12 -14, gives us a -2 overall. So our chromium here being oxidation state, again, a +6, not +12, but +6. And our oxygen being -2, and once again, not -14. Any questions on how to properly assign oxidation states or numbers? Yeah. Obviously, understanding how to assign these things are really helpful in determining what is being oxidized, right, and what is being reduced. And by the way, this is why something like nitrate, for example, has a -1 overall charge, because this guy is a -2, and in this case it is a +5, which gives you that -1 overall charge in that arrangement when they are sharing electrons. All right, yeah. Yeah. If it was nitrogen by itself, it would have 0, right? Unless it was combined with something else. So there's other things that go with it, along with things like formal charge and things like that, that sort of contribute to how the electrons are being shared. But we do know overall nitrate has a -1 charge, and we know oxygen would be -2 in that case, so it has to be a +5 charge to get us to that -1 charge. Yeah. And again, it has a lot to do with, in the case of nitrate, there's like a double bond and a single bonds, right? That happens in that one. And so those double bond electrons are moving around. So it doesn't fully deplete, you know, like nitrogen equal to the oxygens in that case because of those double bond electrons that are moving around. Other questions? Okay. So the other thing I want to go over again, just to make sure everybody's on the same page. And I know everybody's kind of said they remember this stuff, so we just hope so. So when we balance sort of basic redox reactions, like we talked about at the very beginning here, really the one thing that you need to do is just simply make sure that you have the same number of electrons in each half reaction, and then you just add them back together. So in a basic sort of redox problem, that's basically all you got to do. Same number of electrons and add them together. But sometimes we want to balance these in a little bit more complicated solutions where it's maybe an acidic environment or a basic environment. And to balance these redox type reactions, it does take a few more steps along the way to help us get there. So we're going to go through this one, and we'll do it in acidic first, and then we'll switch over and talk about how you could go to basic afterwards. So if you were to balance this redox reaction here in acidic conditions, probably one of the good things or first things that you might want to do is sort of figure out what is going on in terms of who's being oxidized and who is being reduced. So clearly this is +2 and this guy is +3. The two irons that we see there. Is the iron being oxidized or reduced? Is being oxidized, is becoming more positive. And again, if you kind of went on the number line, it's going from 2 to 3 in that direction. By default, that would mean the dichromate is actually being reduced. And we just did this guy, which this guy is +6, the chromium. And the chromium over here is +3. So again, for the chromium, is starting at +6, heading to +3, going in the more negative direction and being reduced. So it's a good idea to keep those things in mind and sort of identify, you know, what is going on and who's being oxidized and who's being reduced. And this guy is being reduced. By the way, that would mean my oxidizing agent would be the dichromate here would be my oxidizing agent, and my reducing agent here would be the iron, obviously. So once you have that all arranged, you just want to split them off into the two half reactions, and it's pretty simple. Take the two things that have the same elements in it and put them together in a reaction. So first half reaction would be iron 2 going to iron 3. Second half reaction would be a little dichromate going to chromium 3. Once you have them split off into your half reactions, which we obviously know now that this is our oxidation, right? And this is our reduction. You want to balance the equations like you normally would balance it. You want to balance all elements except for hydrogen and oxygen. So except for hydrogen and oxygen, you want to balance everybody, make sure you have the same number of elements. So for iron, we have 1 on each side, so that's good to go. For the chromium, we got 2 on the left, but only 1 on the right. So just like a normal balancing equation, we would put a 2 there to do that. Once you've balanced every other element besides oxygen and hydrogen, now you want to balance the oxygens. And the way that we balance oxygens in this type of method is we balance the oxygens by adding water to balance the oxygen. The problem, though, is if we add water to one side to balance the oxygen, we are also adding 2 hydrogens, right, every time we add water. So to make sure that we don't screw up the hydrogen count, we then add also 2 H pluses to the other side. So whatever side needs the water, you add it to get the correct number of oxygens. And then to the opposite side, you need to add 2 H pluses for every water that you added to make sure everything remains balanced. By the way, if you find yourself in an equation where you're starting out just off the bat with more hydrogens on one side than the other, you could just add some H pluses to the other side to balance them out, and everything will be okay. So in the case of the iron, there are no oxygens, so we don't have to worry about there. But in the case of the dichromate, there are 7, which means to the right-hand side, we need to add 7 waters. And again, that is going to balance our oxygen. Because we added 7 waters to the right, we need to add 14 hydrogens to the left-hand side, and that's going to balance out our hydrogens. Any questions up to there? Once we balance all the other elements, once we balance oxygen and hydrogen, the next thing that we want to do is balance the overall charge on each side of these half reactions. And we're going to balance it by adding electrons to balance out the charge. My best piece of advice is just take the overall charge on each side. Why reinvent the wheel and do each one individually? Because that's what the overall charge tells you, is the individual oxidation states all added up. So when I look on the left-hand side of the first one, that is +2. Right-hand side is +3. So since I'm adding a negative electron, I do need to add it to the right-hand side, 1 electron. That gives me a grand total of +2 on this side to match the +2 that we have on the left-hand side. Any questions on that there? Now, on the bottom one, again, I got like a +14 happening here for the 14 H pluses. And I'm not going to worry about individually chromium and all that. The overall thing there is -2. That gives me a +12 sort of happening on the left-hand side. On the right-hand side, that's 2 times 3, which is +6. That means to the left-hand side, I need to add 6 electrons. The 6 electrons plus the +12 gives me a +6 on the left to match my +6 here on the right-hand side as well. Any questions on that there? Now, I could also know by taking the time to figure out what is being oxidized and what is being reduced to make sure I didn't screw up, maybe. Since the top one is the oxidation half reaction, I did add my electrons to the correct side. It should be on the product side, so that's good. And because the bottom one is the reduction, I also added my electrons to the correct side, which is the reactant side. That's also good. If you ever find yourself adding electrons to the same side of the arrow in the opposite half reactions, then you definitely screwed up, for to say a nice word, I guess there. You messed up on that one. Once we add the electrons, we're ready to add each half reaction back together. But once again, before we could add them back together, we do need to make sure we have the same number of electrons in each half reaction. And in this particular case, we obviously have only 1 in that top one. So I'm going to multiply the top one there by 6 in this case. And at this point, I'm just going to recopy that there. That gives me 6 of the iron 2 goes to 6 of the iron 3 plus 6 electrons. That then gives me on the bottom, which I did not change, 6 electrons plus 14 H pluses plus our Cr2O72 minus, 2 of the Cr3 plus, and our 7 waters at this point. Now that I have the same number of electrons in each half reaction, I can add these together and cancel out whatever is the same on opposite sides of the arrow. And in this case, I think it's just going to be the electron. So electron there and electron there cancel. And I believe that is it. So everybody on the left stays on the left. So gives me 6 iron 2 plus 14 H pluses plus our Cr2O72 minus goes to our 6 iron 3 plus our 2 Cr3 plus and our 7 waters there. And if I did not screw up, we'll hope for the best here. This should be balanced basically two ways. It should be balanced like a normal equation, which means you have the same number of elements on both sides. So I got 6 irons on the left, 6 on the right, 14 H's on the left, 14 on the right, 2 CRs on the left and 2 on the right, 7 oxygens on the left and 7 on the right. And it should also be balanced overall charge on each side. Doesn't have to equal 0, but should have the exact same charge on each side. On the left-hand side, I have 6 times 2, which is 12. Positive 12 plus positive 14 is a lot. That's plus 26. Minus 2 is plus 24 on the left-hand side. Right-hand side is plus 18. And plus 6 is whatever I just said there, plus 24, I hope on the right-hand side as well. And this would be a balance in acidic solution. Any questions on that there? This sounds familiar, yes? Now, if we wanted to do basic conditions, my recommendation is just to do an acidic conditions like we just did. And at the end, what you would do is add some hydroxide to both sides. So let's say we wanted to do this in basic conditions. And let me actually just copy that. So that was 6Fe. 6Fe2 plus 14H pluses. Put that there, 14H pluses. CR207. 6, 2. 6 of these plus 2 of these. Lastly, 7 waters, I think it was. Yep, 7 waters. All right, so if you balance this guy here in acidic conditions, but you really need it in basic conditions, you know, I would do exactly what we just did. It is sort of the easier move. And what you want to do now is actually add OH minus to both sides equal to the number of H pluses you have. So we're going to add OH minus to both sides equal to the H pluses. So in our case here, we have 14 H pluses. You would do 14 OH minus added there. And I'll just go underneath here, 14 OH minus is to this side. The side that has the H plus and OH minus, they will come together to make water. And you will end up with 14 waters as a result of that, plus 6 Fe2 plus CR2O7 2 minus. 6, nothing else here changes yet. Plus our 14 OH minuses. And what usually will happen in this case is you will have some waters that you can reduce down. So I got 7 waters on the right, can reduce this down to 7 waters on the left, giving us our final balanced equation in basic conditions. Which looks something like this. And once again, this guy should also still be balanced both ways. We got 14 hydrogens once again on both sides, 7 oxygens, and 7 is 14 plus the 14 on the right, 6 irons and 2 chromiums on both sides. Overall charge on the left is plus 12 and minus 2 is like the plus 10. Plus 18 on the right there, and 6 more gives us a plus 24. Minus 14 is a plus 10. So we're balanced on both sides. So that's really, I think, the easiest way to convert it into a basic. It's just to do acidic first and then convert it over. Years ago, they used to teach people to do it like when you add the electrons, or before you add the electrons, you could add the hydroxide at that point. But personally, that is a lot more canceling out you got to do in the middle of the problem, stuff like that. Probably a little bit more room for error. But an older method I haven't seen too much done lately is like right before you add the electrons, after you balanced everything, you could add the hydroxide to both sides. You could do it that way and it works out perfectly fine. You just got a lot of reducing of waters that you got to kind of deal with in the middle of all that, which again could lead to a problem. Any questions on how to balance these equations? All right. By the way, we know that the bottom one is in basic solution because I see what in the final reaction? Hydroxide. The original one before I added the hydroxide was an acidic solution because it had the H plus. Yeah. 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 It's a good question. I would say probably for our purposes here, most of the time it would just be kind of given to you. There are certain things, certain products that can happen, you know. If you're in the laboratory, sometimes based on the observation of the color that you see when you do it, you know what is being formed. So for example, at a school I teach at, they do a redox experiment where they have, for example, Mn has like 6 different oxidation states. And based on sort of the color that they see as a result of doing the reaction, we'll tell them, hey, you know, it's the Mn+2 or it's the MnO, you know, and stuff like that. So there are some common ones based on what you're putting together that you could pretty well predict what you would get. But for our purposes, you probably would be started with the equation there, the Fe 2 plus the dichromium, what's on the other side, or just told what it is in words, and you just kind of put it together. But in an experimental type thing, you could do it based on observations because you know, different oxidation states, especially things like transition metals, have different colors and stuff like that. And based on sort of the colors that you see, you could kind of predict that. And since a lot of these reactions have been done a lot, you know, you could basically know if you put these together that, you know, this is really the guy that you should get out as a result of it. But for us, you probably will start with obviously the equation. You want to start with that. If you did, you would have the other guy there as well. Like it would tell you, you know, it would tell you that you would produce chromium-3 or something like that. So you would have it all to start with. Other questions? All right, why don't we try one? I did one. Why don't you make sure you could do one? I'll just scroll this across. This is what we just did in case you want a prettier picture of what we just did. When you're watching the video while you're going to sleep, putting yourself to sleep, whatever it may be. I hope it agrees with what I got at the end. That would be good too. All right. All right. So I want you to, so for example, your question would be something like this, where it would say like the products, for example, is I2, and you know, if it wasn't given to you, so you would have pretty much everything there that you could get to this equation, you know, from it. All right. So starting with this one, let's balance it. What are we doing it? We're balancing it in. Does it say? Okay, sure. Sounds good. Basic solution, it says. There it is. There it is. You do, yeah. It's a good move. All right, go for it. Balance it up. Doing so. Once again, if you want, you can just break it off into the half reactions. So we'll start with I minus, which is obviously related to I2, and a little permanganate there to our MnO2. So we can also maybe figure out what's going on. So our iodine is -1 and our I is 0. So again, on our number line here, it is going from -1 to 0. It is being oxidized in this case. By default, this guy should be reduced, and we can figure that out because the oxidation state of Mn in this case is +7, I think. Yeah. Oxygen is -2, and there's 4 of them, which gives you -8. +7 gives you a -1. The Mn on the right-hand side is +8. It is +4. Each oxygen is -2, gives you -4 and +4. That means that our Mn is going from +7 down to +4 in that direction, becoming more negative and going through reduction. Any questions on that part there? All right, so now that I scribbled all over that, let me rewrite these guys. Go this way. And we'll do a little MnO4. MnO2. So next we want to do, right, is balance everybody besides oxygen, hydrogen, which in this case means we do need to put a 2 there. And I think that's it. Now we can move to balancing the oxygen. Obviously, there are no oxygen there in the first one. Left-hand side on the second one has 4. Right-hand side has 2, which means we do need a couple of waters over here to get us the right number of oxygens. Thus, we also do need to add, I'm not going to say 14, how about 4 H pluses to the other side there? 4. Now that we balance the hydrogen and the oxygen, we would then want to balance out the charge by adding electrons. And in this case, again, we want to add it to whichever side needs the negative. And in the top part, we have a -2 on the left, a 0 on the right, which means the right-hand side needs a couple of electrons. That is good because this is our oxidation, right? So our electrons ended up there in the right spot. On the bottom here, that is +4. That is -1 for a grand total of +3, if I did my math right there. That is 0 on this side. That means actually the bottom guy needs 3 electrons. Any questions on that so far? We are ready to add these guys back together, but clearly we got some electron situation. So common number there is 6. In this case, we actually need to multiply both by a number, top guy by 3, bottom guy by 2. So if I do that, and I'm going to rewrite underneath, I think we will get 6I minus goes to 3I2 plus 6 electrons. Multiplying the 2 to the bottom one gives us 6 electrons plus 8 H pluses plus 2 of the MnO4 minus. Taking our 2 still across to the other side there, 2 of these guys, and 4 waters at this point. Now that we got the electrons all working good for us here, we can add them together. And it looks like it is going to be just the electrons here that cancel. And that will leave us 8 H pluses plus 2 MnO4 minus plus 6 iodides. Go to the other side, 3I2 plus 2 MnO2 plus 4 waters. Any questions so far? If I wanted acidic, I could put a box around that and hopefully I'm good. I've got 8 on both sides of hydrogen, 2 Mns, 8 oxygens, and we have 6 iodines. Overall charge on the left there is a lot. I don't know that it's like -8 and +8, which is 0, and 0 on the other side. So that's all good. What I'm going to do now is obviously turn it into basic. So we're going to add an equal amount of OH minus to both sides equal to our hydrogen, which is 8. And what I'm going to do so I don't have to flip back and forth is I'm just going to erase some of the top part here and just kind of do it up here, I think. Oh, I got somewhere I could see it. All right, I'll get rid of some of this stuff here, do it here. All right, so adding my 8 OH minuses to the left to go with my 8 H pluses plus my 2 MnO4 minus plus my 6 iodine goes to the other side, which has 3I2 plus 2 MnO2 plus 4 waters. Obviously, these guys are now going to become 8 waters, which will get rid of 4 from that side and leave us 4 on that side. giving us a grand total of everything left over at this point of 4 waters plus 2 MnO4 minus plus 6 iodides go to 3I2 plus our 2 MnO2 plus our 8 OH minuses that I forgot to throw over there originally. Should be there as well. That's much better. There we go. And now we should be balanced here in the basic solution. Obviously, you should add the OH minus to both sides there. Again, we have 8 hydrogens on both sides, 8 oxygens, 2 Mns, and 6. Overall charge on the left there is now -2 and -6 is -8. If I go with the -8, that's on the other side, and we are balanced at that point. Any questions on balancing these redox reactions? All right, we're professionals. Yes, I like it. All right, good times. All right, then let's get really into this chapter. Then we'll kind of skip through these. In case you want some more practice, there's a couple more you could do if you like. All right, so what we're going to talk about now is galvanic cells. And galvanic cells are really redox reactions that occur. This is a traditional setup for a galvanic cell in the laboratory. You got a couple of beakers. You have a couple of electrodes that are connected by a wire. A lot of times you got a voltage meter there. And on the left-hand side in this particular diagram is what is known as the anode side. And on the anode side, that is where oxidation occurs. So that is where the loss of electrons occur. And in this case, you typically do have a solution that contains an aqueous ion of what your electrode is. So in this case, that's a zinc electrode solid. Floating around the solution should be some aqueous zinc. And basically, as it loses electrons, the solid zinc goes for a swim and goes into the water and becomes aqueous zinc with a +2 charge. Those electrons travel through the wire here, through the voltage meter, gives you a voltage reading, and it goes to the other side of a galvanic cell, which is the cathode side, and that is where reduction occurs. And the similar thing is on this side, we have an electrode. In this case, this is a copper electrode. Also in the solution, some copper ions that are floating around as well. And that is because when the electrons come in, they combine with those copper ions that are floating around the solution, and they actually decide, I've had enough swimming for today. I'm going to go out of solution and become solid in that case. So this is the redox reaction that is happening, oxidation on the left, and that is our oxidation half reaction. It is the solid zinc losing a couple of electrons and going into the solution. Those electrons are traveling to the other side, where it combines in the reduction half reaction with the aqueous copper to go from a +2 to no charge in that case. If you add both of these half reactions together, you get the overall net reaction that's happening, which is the zinc going from an oxidation state of 0 to +2, which is being oxidized, and copper going from a +2 to 0 oxidation state being reduced in this reaction. There's also a really important component as well, which is a salt bridge. Salt bridge connects the two beakers in a galvanic cell. It is usually filled with some type of electrolyte solution, which is something that will break apart into ions. And in this case, it is potassium chloride. So what is the importance of this? Well, first off, we do have the negative ion heading over to the anode compartment, while the positive guy is heading to the cathode department. So the purpose of this is to keep everything flowing. There is a potential difference, kind of like the cathode side, a little bit more positive to kind of pull those electrons to that side. Now, if we did not have the salt bridge and we just let this thing run, what's going to happen in terms of charge on the left-hand side in this beaker? If we just ran this, no salt bridge, what is basically happening here? These ions are jumping into solution, right, and becoming what type of charge? Zinc becomes positively charged. So if you let this thing run, you're just building up a lot of positive charges, right? And that's problematic if you want electrons to leave, because then they're going to be attracted to that beaker, right? And they're not going to go anywhere at that point. So the purpose of the salt bridge, and this is why the negative guy is going down there, the negative guy is going down there to keep the positive charge from getting too high. Same thing happens on this side, on the right-hand side. What's going to happen on the right-hand side if you don't have the salt bridge is the positive guys are going out of solution, right? Which means you're actually going to get a buildup of negative charge if you don't have that salt bridge. So if you didn't have the salt bridge, you would get a buildup of positive charge on the left-hand side and negative charge on the right-hand side, which means those negatively charged electrons aren't going to go anywhere. They're not going to want to go anywhere near that. So that is why the salt bridge here, the positive guy is going down to cut down on the negative buildup over here and keep a little bit more positive on that side to keep those electrons from really going. So the purpose of salt bridge really is to keep this thing really functioning. Otherwise, without it, you're just going to kind of build up the wrong charges on each side, and that's going to prevent those electrons from obviously traveling, and obviously nothing's going to be done in terms of work. Any questions on that there? So this is a spontaneous reaction. Electrons always transfer from anode to cathode in this case. And when we talk about galvanic cells, we're oftentimes asked to calculate a couple of different things, which for the most part is kind of the same thing in each case. And here's an actual hookup of that galvanic cell, and you can see you got a positive voltage there of 1.10. As we'll talk about, positive voltage is good, negative voltage not so good. Very much like a battery, right? If you put it in backwards, not much happens. You got to put it in the right way and get the electrons flowing in the right direction. The difference in electric potential between the anode and cathode is what's referred to as the cell voltage. And a volt is basically 1 joule of work per coulomb of charge transferred. A coulomb is a unit of electrical charge. It is also sometimes referred to as EMF or electromotive force or cell potential. And problems, they sometimes ask you to calculate all those things, but really what they're asking you to calculate is the cell voltage, basically, and when they're asking you to calculate any of those things. And it's really sort of that driving force to pull those electrons from one side to the next. And again, you can kind of think of the cathode as being a little bit more positive to help draw those electrons, you know, over to that side. This is our overall reaction that we talked about, and another way to represent a galvanic cell is to use a cell diagram, which is this guy right here, the whole bottom thing. And a cell diagram is basically anode to cathode. And if you ever need to go from, say, the cell diagram to the equation, there's usually a very simple formula. First guy there is the reactant. Next guy is the product. That's the reactant, and that's the product. So as you can see, if you look above on the equation, that's the reactant. Zinc with the +2 is the product. Copper with the +2 is the reactant, and copper with no charge is a product. So that is sort of the order. That is why there's a single line between that, sort of reactant to product sort of compartment. The double line here represents the salt bridge. And if it is solutions, they will sometimes put the concentration in there, so 1 molar. It is possible to have a gas involved, so sometimes you'll see pressure involved in there. And as we'll talk about here shortly, sometimes they use sort of a inert electrode because there is no physical electrode for a gas, right? There's like no metal you could kind of put up there. That's the gas version of it. So sometimes they'll use things like platinum or something like that, which is used, or carbon or graphite, that is used as sort of the physical electrode when you kind of make a cell that involves gases. Any questions on that there? Okay, we're going